In the world of computers, there are these problems that seem to have a hidden secret. On the surface, they look almost identical. But for a machine, well, one is a gentle walk in the park, and the other is like trying to climb a mountain that just goes on forever.
Okay, let's look at a classic example. If you ask a computer to find the shortest, simple path between two cities on a map, it'll spit out an answer almost instantly. It's a solvable, efficient problem. But then, you make one tiny little change. Ask for the longest, simple path. And suddenly, that same computer could run for centuries and still not find a guaranteed answer. The problem just breaks.
So what is that? What's this invisible line that separates the problems we can solve from the ones we can only stare at in wonder? Well, today, we're going to go on a quiet climb together to understand this really fascinating boundary in computer science. Let's start our journey at the base of the mountain, in a world that feels really familiar and orderly. This is the world of problems that, for a computer scientist, are considered easy. This world is called P, and P stands for polynomial time. Now, I know that sounds a little technical, but all it really means is that as a problem gets bigger, the time it takes to solve it grows at a nice, predictable, and manageable rate. We call these problems tractable.
A great way to picture a problem in P is just thinking about sorting a deck of cards. Whether you have 52 cards or 500 cards, if you have a good system, you know you can get it done pretty efficiently. There's a clear step-by-step process that just works every single time.
So this is a place of order, of predictability. It's a world where our algorithms give us clear, timely answers. It's a place of beautiful, reassuring clarity. We're on solid ground here. Okay, now let's take a step up into a much larger and honestly more mysterious landscape. This is the world of NP. NP stands for non-deterministic polynomial time, which again sounds super complex, but the core idea is actually really simple. It's the group of problems where if someone just hands you a possible solution, you can check if it's correct, and you can do that check very quickly. So notice the big shift here. We're not talking about finding a solution anymore, but just verifying one. And the classic Sudoku puzzle is the perfect way to get this. Trying to solve a hard Sudoku from a blank grid, well, that can take a long, long time, right? But what if I give you a completed grid? How long does it take to check if it's right? Maybe a minute or two. You just go through and check that every row, column, and box has the numbers 1 through 9. See? Hard to solve, but really easy to check. That's a problem in NP. This brings us to a really cool relationship. It turns out that every single problem that's easy to solve, every problem in P, is also easy to verify. And that makes perfect sense, right? If you can find an answer quickly, like sorting that deck of cards, you can definitely check a proposed solution quickly. You could just solve it yourself and see if you get the same answer. This means that the entire world of P fits completely inside the bigger world of NP. And this leads us to what is probably the biggest unsolved question in all of computer science, and one of the most important in all of math. Does P equal NP? Is every problem that's easy to check also easy to solve? Most computer scientists think the answer is no, but nobody has ever been able to prove it. And so here we are, sort of peering through a keyhole at this vast, unknown universe, a world just filled with these tantalizing possibilities, where the very limits of what we can compute are still a beautiful and profound mystery. Okay, we've made it. We've reached the highest, most rugged part of our climb. This is where we find the true giants of complexity theory, the NP complete and NP hard problems. Let's start with NP complete. Think of these as the hardest of the hard problems inside of NP. They are problems that are definitely in NP, so we know their solutions are easy to check, but they just seem to resist any and every attempt to be solved efficiently. And here's their mind-bending, almost magical property. All of these NP-complete problems are linked together. If someday someone finds a fast, polynomial time algorithm for any single one of them, it would be like finding a master key. That one solution would unlock a fast solution for every single problem in NP. It's this incredible domino effect. And what's so wild is that these problems show up everywhere in totally different fields. It can be about optimizing delivery routes for a shipping company, designing complex computer chips, breaking cryptographic codes, or even just figuring out the best way to pack your suitcase. On the surface, they look completely unrelated, but deep down, they're all members of this same family of profoundly hard problems. This diagram really helps put it all together.
You can see the world of P, our easy problems, tucked safely inside the bigger world of NP. Then you've got the NP complete problems, which are the toughest challenges right there at the edge of NP. But what about that outer circle, NP hard? Well, this is where things get even wilder. An NP hard problem is at least as difficult as the hardest NP complete problem. It might be even harder, maybe so hard that we can't even check a solution quickly. It's the true wilderness at the edge of what we can compute.
So, after all this theory, you might be asking, why does any of this matter in the real world? What's the point of knowing that a problem is practically impossible to solve perfectly? Because knowing a problem is NP complete isn't a dead end. It's actually a signpost. It's a message that tells you to stop wasting your time searching for a perfect, lightning-fast solution that probably doesn't exist. And that piece of wisdom has saved engineers and scientists countless years of fruitless work. So this gives us a really practical roadmap. When you run into one of these monster problems, the first step is to recognize it for what it is. Then you simply change your goal. You stop hunting for the perfect answer. And instead, you build what's called an approximation algorithm, a clever program that finds a solution that's good enough and does it in a reasonable amount of time. It's this beautiful trade-off. You give up on perfection to achieve something that's actually practical and useful. And maybe that's the real beauty of this little climb we've taken. It teaches us that sometimes the most profound progress we can make comes not from finding the perfect answer, but from gracefully and wisely understanding the limits of what we can perfectly know.